Hello students. Today we are going to have a one short session on coordination compounds, chapter coordination compounds as per student request. In this session, we will be discussing all important areas of this chapter, including some PYQs. Though we cannot discuss all the PYQs, some of the PYQs will be including in this session. Hi, I am Prasanna and welcome to my platform, ChemSmart. When you come to coordination compounds, you should understand that it is a part of modern inorganic chemistry. It falls under modern inorganic chemistry. The scientist Alfred Werner, a Swiss chemist, he is known as the father of coordination chemistry because he was awarded Nobel Prize for proposing the octahedral configurations of transition metal complexes. That's why he is known as the father of coordination compounds. And we are going to discuss what are the important areas in this chapter. Starting with the intro itself, which contains some board questions. What are the important coordination compounds which we come across in our day-to-day life? Number one, chlorophyll. You know, it is a coordination compound of magnesium, the green pigment in plants, chlorophyll. It is a coordination compound of magnesium. So they can ask you what is the central atom in chlorophyll. Similarly, hemoglobin. Hem means iron. Hemoglobin is the red pigment in blood. It is a coordination compound of iron. Hem means iron. Then, vitamin B12. In biomolecules chapter you have studied, vitamin B12 is also known as cyanocobalamin, which is anti-pernicious anemia factor. Cyanocobalamin. So what is the central atom in vitamin B12? Cobalt. That's why it's called cobalamin. Then cisplatin. It is used in medicine. It is used in cancer therapy. So as the name indicates, cisplatin. So platinum is the central atom in that coordination compound. Clear? So all these are previous board questions. You have to prepare them, though it is coming in the introduction area. Now coming to Werner's theory. I have already told you Werner has done a lot of experiments and a lot of studies about coordination compounds, and based on his findings, he has put forward his theory about coordination compounds. And all the postulates of Werner's theory are there in your textbook. You have to learn all of them properly because it is asked in, I won't say it's a repeated board question, but it is asked in some years, better to prepare them. We'll have a quick recap of what are the postulates in Werner's theory. According to Werner's theory, in a coordination compound, the metal shows two types of valencies. First one is primary valency, which is normally, primary valencies are ionizable. Metal shows two types of valencies, primary and secondary. Primary valencies are ionizable and they are normally occupied by the negative ions, okay, which will be ionizable. Secondary valencies are occupied by, they are not ionizable, they are occupied by neutral molecules or negative ions. Actually, secondary valencies are occupied by ligands. That's it. Okay? They are not ionizable. And then, you know, the secondary valencies or the groups occupying the secondary valencies, when connected to the central metal atom, they have a definite geometry, okay, definite stereochemistry about the central atom. That is called, that shape, that will be called coordination polyhedron. Okay? And the ions which come outside the square bracket when you write the complex, okay, outside the coordination entity. Whatever is there in the square bracket, it is called coordination entity, and those which come outside the coordination entity, they are called counter ions. So you please make sure to learn all the postulates as per how it is given in the textbook. Clear? I don't want to spend a lot of time on that. And this question is a repeatedly asked board question. Difference between double salt and complex. Common question in papers. Double salts You look at these compounds, okay? They are double salts. For example, here you can see in carnallite, it is containing KCl and MgCl2. There are two components, two salts. Potassium chloride itself is a salt, MgCl2 is a salt, so they are called double salts. And it is having water of crystallization, water of hydration, 6. Similarly, more salt, you have used it in volumetric analysis this year in class 12. In permanganometry, you have taken potassium permanganate in the burette and more salt in the conical flask, right? So it is ferrous sulfate, ammonium sulfate, 6 water. So there are two salts in it, ferrous sulfate and ammonium sulfate. It is a double salt. That is why more salt is also known as ferrous ammonium sulfate. Okay, ferrous ammonium sulfate. Then potash alum. You know, alum is used to clear muddy water. When you add alum into muddy water, the clay particles will get coagulated. You might know about it. And the commonly used potash alum. What is potash alum? Potassium sulfate, aluminum sulfate, 24 water. There are two salts in potash alum, potassium sulfate and aluminum sulfate. These are called double salts. And what is the speciality of the double salt? I will take an example. Suppose we take carnallite, KCl, MgCl2, 6H2O. This is your carnallite. If you put it into water, what will happen? KCl will dissociate into K plus and Cl minus. MgCl2 will dissociate into Mg2 plus and 2Cl minus. And rest is water of crystallization. That means each component of the double salt will undergo complete ionization. That is, the solution of carnallite in water will contain potassium ions, chloride ions and magnesium ions. Chloride is common. Okay? So all these ions will be present in the solution and the solution will answer the test, chemical test for all these ions, potassium, chloride and magnesium. That is how double salts work. When we come to a complex, the complex will not dissociate completely into its constituent ions. That means if you take the example of K4FeCN6, that is potassium ferrocyanide, when you put it in water, it will dissociate into the counter ion potassium and the complex ion FeCN6 4 minus. So you'll be getting 4 potassium ions and 1 ferrocyanide ion. But this ferrocyanide ion will not further dissociate into ferrous ions and cyanide ions. That means the resulting solution will not contain ferrous ions and cyanide ions. It will contain only these ions. So the test will be negative for which all ions? Ferrous ions and cyanide ions. It will be answering only yes for these ions. Clear? That's the difference between double salt and complexes. A repeatedly asked board question in papers. Prepare it well. And they have a common feature also. That is, double salt and complexes, they have a common factor. And what is the similarity? Both double salts and complexes are formed by the combination of two or more stable compounds in stoichiometric ratio. That is the common feature between these two. Clear? Now, coming to some important definitions in coordination chemistry. All these definitions are clearly given in your textbook. So I haven't detailed them here. We'll have a quick discussion. You learn all the clear definitions, exact definitions from the textbook. Okay, they are important for the board examination. Now let us discuss them quickly. What is meant by coordination entity? What you write in square bracket, that is the coordination entity. For example, let me take the same thing what we discussed right now. K4FeCN6. If you take this complex compound, what is there in the square bracket? that is called coordination entity. What is standing outside the coordination entity, that is called counter ion. Sometimes counter ion will be positive if the complex part is negative, or if the complex part is positive, counter ion can be negative. You know about all these things. So this is the counter ion. Here iron, it is in +2 state here. That is the central metal ion. Iron is the central metal atom and Fe2 plus is the central metal ion. And cyanide ions are the ligands. And iron is connected to 6 cyanide ions. Each cyanide will be making one covalent bond, one dative bond or coordinate covalent bond with the central metal ion Fe2 plus. So the number of bonds, number of ligating groups in a ligand, that is called its denticity. So Cn minus is a monodentate ligand or a unidentate ligand because there is only one binding atom in this one. Okay, Cn minus. So Fe2 plus is connected to 6 cyanide ions. Each cyanide ion is making one bond with the central metal ion. So we can say the coordination number here is 6, or the coordination number of Fe2 plus is 6. That means it is an octahedral complex because its coordination number of the central metal ion is 6. Clear? Now, when you come to these things, so you know what is meant by the coordination entity now. And what is central metal atom or ion? You know that? That is the atom or ion to which the ligands are connected. That is called the central metal atom or ion. Then ligands, they are either negative ions or neutral molecules with lone pairs. They are actually Lewis bases which will get connected through dative bond to the central metal ion or atom. And they are called ligands. There are different types of ligands. Like I told you, they are based on their denticity. Denticity means number of ligating groups in a ligand. They can be classified into unidentate where the denticity is 1, didentate or bidentate where the denticity is 2. For example, if you take oxalate, COO minus, COO minus, here denticity, this is one ligand but there are 2 donor sites. So it is a bidentate ligand. You know about EN. EN is ethane 1,2-diamine. That is the IUPAC name, or ethylene diamine is the common name. Here one EN has 2 donor sites. So it is a bidentate ligand. Now if you replace these 2 hydrogens by acetate groups, CS2, it is actually CS3COO minus, but you are connecting it by removing one hydrogen. So here also one CS2COO minus. Then if you replace these 2 by CS2COO minus and CS2COO minus, then we get something called EDTA, 4 minus. What is this? Ethylene, it was ethylene diamine. You replace the 4 hydrogens by 4 acetate groups. So it is ethylene diamine tetraacetate. Why it is 4 minus? COO minus, COO minus, COO minus, COO minus. There are 4 negative areas, so we give the charge 4 negative. But what is the denticity of this EDTA 4 minus? These 4 donor sites plus 1 nitrogen with its lone pair here, 1 more nitrogen with its lone pair here. So totally 1 EDTA 4 minus can make 6 bonds at the same time with the central metal atom or ion. So this is a hexadentate ligand. So we would say for Cn minus denticity is 1. It is a unidentate ligand. For oxalate and En, denticity is 2. That's bidentate ligand. And EDTA is a hexadentate ligand. Normally when the denticity is more than 2, we call them as polydentate ligands. Clear? Okay. Now, when you come to the coordination number, I told you coordination number is same as the secondary valency. And here coordination number of iron is 6, for example. Then coordination sphere, same thing what is there in the square bracket. That area is called coordination sphere. Then coordination polyhedron. That means the shape which is formed or the stereochemistry of the complex when the central atom is connected to different ligands. What is the shape what you get? That is called the coordination polyhedron. That can be octahedral, tetrahedral, square planar, etc. Now, oxidation number of the central metal atom, that is here iron is in +2 state. Iron is in +2 state. So, +2 is the oxidation number of iron here. How do you define it? It is the charge which will be left out on the central metal atom when all the ligands are removed from the complex with the electrons which were given to the central metal atom. When you remove all 6 cyanide ions with their electrons what were donated to iron, what is the charge on iron? That is its oxidation state. Clear? Now, what about homoleptic and heteroleptic complexes? A complex in which same type of ligands are there, same type of donor atoms are there. They are called homoleptic complex. Here, for example, this is a homoleptic complex because all are cyanide ions. But let me take another example. Let me take CO, NS3 3 times Cl3. Look at this complex. Here, cobalt is ligated to 3 ammonia molecules and 3 chloride ions. So, coordination number is 6, but there are different ligands getting ligated or connected to the central metal ion cobalt 3+. So, this is a heteroleptic complex, different donor atoms, whereas this is a homoleptic complex. Clear? Now, moreover, when you come to ligands, you have to know about something called ambidentate ligand. What is meant by ambidentate ligand? The same ligand can ligate or bind through 2 different donor atoms, but it is not at the same time. It can ligate through either one atom at a particular time. Clear? So, we will see some examples shortly. When you come to ambidentate ligand, I would like to explain that in detail. When you come to ambidentate ligand, let us take nitrite ion. You know, nitrite ion has 2 different donor sites within. One is it can ligate through N. Okay, it can ligate through N. Then this will be the binding atom. But it can ligate through O also. Then this is the binding atom. That means it has 2 donor sites within. But it will bind through only one atom at a time. For example, if it is binding through N, then that will be called nitrito N when you write the IUPAC name. If it is binding through O, then it will be called nitrito O in IUPAC nomenclature. Clear? So, NO2 minus is an ambidentate ligand. It has 2 donor sites in the same ligand. Another one, thiocyanate, SCN minus. It can ligate through S, then it is called thiocyaneto, or it can even ligate through N, then it is called isothiocyaneto in nomenclature. So, this is an ambidentate ligand which can ligate through 2 different donor sites, one at a time. So, this is thiocyaneto, this is isothiocyaneto. Clear? So, this also you have to know. It's an important definition commonly seen in board papers. Please do prepare from your textbook. Right? Now, coming to outer orbital complex and inner orbital complex. What do you mean by outer orbital complex and inner orbital complex? Outer orbital complex, you will be studying about it in detail when we go to valence bond theory of coordination compounds. Outer orbital complex means we are using outer shells S, outer shells P and outer shells D for hybridization. That means like it is sp3d2 in octahedral coordination. If the complex is undergoing sp3d2 hybridization, we would say that complex will be an outer orbital complex because outer D is involved in the hybridization part. What is inner orbital complex then? Inner D is involved. In that case, it will be n-1d, that is the inner D, then outer S and outer P will be used for hybridization. Then example D2sp3. If you come to D2sp3, then inner D is involved for hybridization. So we call it as inner orbital complex. That particular complex will be called inner orbital complex. Clear? Like 4s, 4p, 4d, outer orbital complex. But if it is 3d, 4s, 4p, then inner D is involved, 3d is involved, so it will be called the inner orbital complex. Clear? Now, coming to chelate complex. What is meant by denticity? I have already told you the number of ligating groups in a ligand is called denticity. Now, coming to chelate complex. I told you oxalate has 2 donor sites which will be used at the same time. En, it has 2 donor sites which are used at the same time to ligate to the central metal atom or ion. EDTA, it has 6 donor sites. All can be used at the same time to get bonded to the central metal atom or ion. That means when more than one donor site comes, it will be like the claw of a crab. So chelate means claw, okay, claw-like structure. Hence, it is called chelate complex. When the central metal ion or atom is surrounded by multidentate ligands, starting from didentate ligand, then it will be like the central metal atom or ion surrounded by chelate ligands like the claws of a crab. That is why they are called, such complexes are called chelate complexes. You can see an example here. Suppose I take CO En thrice 3+. CO En thrice 3+. How will you draw it? Look here. I will just draw that complex here. You can understand how it is behaving like a chelate complex. Look here. The central atom is cobalt. And you know En is neutral, so its charge is 3+. Then each En will make 2 bonds. So 2 into 3, 6. That means it is octahedral coordination. Now En thrice. So let one En be here, one En here, and one En here. So this is the complex. You can see it is as if the central metal ion is surrounded by 3 claws of a crab. Like this is one, this is one, this is one. So such complexes where chelate ligands are involved in complex formation, they are called chelate complexes. And what is the speciality of such complexes? Such complexes will be having enhanced stability compared to the non-chelate complexes. When chelate complexes are there, they will protect the central metal atom or ion well from the attacking reagents. That means it will lead to enhanced stability, because if these are all monodentate or unidentate ligands, that complex will be less stable. But when they are chelate ligands and chelate complexes, they will have enhanced stability. Very important for application question. Clear? Okay. So I think you got all these properly, all these definitions. We had a quick recap of what you have learned already in the chapter. Make sure to learn all the definitions thoroughly from the textbook. Okay. Now, coming to chelate effect, what I told you, it is just the definition of chelate effect and the repeated board question what is asked from this area. What is chelate effect? The enhanced stability of complexes containing chelating ligands. It's called chelate effect. And this is the application question commonly seen in papers. COEN thrice is more stable than CONS3 6 times 3+. Sometimes they will ask it like this. Sometimes they will give you these two complexes in the paper and ask you to find out which one is more stable. You have to say which one is more stable and why, the reason. So which one is more stable? Whenever chelate ligands are there, that will have enhanced stability. So this is more stable than this one due to chelate effect. Clear? So practice all these things really well. Now the next topic will be, we are going to discuss IUPAC nomenclature of coordination compounds and how to write structures from IUPAC names. Okay, you have to practice it well. We are going to IUPAC nomenclature. Coming to IUPAC nomenclature of coordination compounds, let us do some latest board questions so that you will get a practice for that area also. So I have selected such board questions, okay, for more practice. Coming to the first one, CrNS3 4 times Cl2 plus. How will you name it? First of all, what you have to do is calculate the charge on the central metal atom. Okay, let us assume that as X. We will calculate X. Ammonia is neutral, so it is 0. Chloride is -1, each chloride. Now let us calculate X. What is X? X plus 0 into 4 plus -1 into 2, -2 is equal to the charge on the ion. If there is nothing written here, you will equate it to 0. Then you are getting X is equal to +3. So we got the charge on chromium as +3. This is what you have to do first. Then we will call the ligands in alphabetical order. You know, ammonia is called amine. AMMINE. Cl being a negative ligand, anionic ligand, you have to end it as IDO as per the latest rule. So it is known as chlorido. Previously it was called chloro. Now it's called chlorido. So what is it? 4 amines. So you have to write tetraamine. Don't leave gap in between. So tetraamine. Then 2 chloride ions are there. So it is dichlorido. Chlorido. Now, should we write it as chromium or chromate? We are revising, right? So you know about all these things. If it is positive or neutral, then you have to end it as the normal name, like chromium. But if the complex is negative, you have to end it as chromate. You have to add the suffix ate. Here the complex is positive, so end it as chromium. So I will write chromium. And what is the charge? What you got when you calculated X value? It is +3. Write that as Roman numeral in parentheses. And because it is ion, it is not neutral, it is ion, better to write it as ion for perfection. Okay? So what is the name of this complex? Tetraamine dichlorido chromium 3 ion. That is the name of this complex. Clear? Great. Now let's go to, so you can see it is asked in 2020 for 1 mark. Next one. Now let's come to the next question. COEN twice H2O CN 2 plus. Let us use the same method. You know, we have to calculate the charge on cobalt, which is X. En is 0, water is 0, cyanide is -1. So let us calculate what is the charge on the central atom cobalt here. So it is X plus En is 0, so 0 into 2, 0, plus aqua, water is 0, plus cyanide is -1 and there is only one cyanide ion, so -1 is equal to the charge on the complex, which is +2, so it is equal to +2. So you are getting X as +3. Now let us call the ligands in the alphabetical order. This is ethane 1,2-diamine, which starts with E. This is aqua starting with the A. This is cyanido starting with the C. So call them in the alphabetical order. Who should come first? Water should come first, A. So it will be aqua. Then comes C. So it is cyanido. Cyano is the old usage. So use cyanido. Aqua, cyanido. Then there are 2 ENs. So we have to use bis here. because already in the name of en, ethane 1,2-diamine, di is coming. So we are not using again di, ethane 1,2-diamine. We have to use bis. So bis, then put a parenthesis, then write the name of en, which is ethane 1,2-diamine. Only one M, take care. Ethane 1,2-diamine. Then cobalt. Cobalt. What you got is 3. So write that in Roman numeral in parenthesis. And it is an ion. So just write ion. So the IUPAC name of this complex is aqua cyanido bis ethane 1,2-diamine cobalt 3 ion. Clear? Now let's take another question. This is 2019 board question. Most of the years there will be naming questions from coordination compounds, or they will ask you to write a structure from IUPAC name. Very common. Now the next one is again a complex of cobalt. Chloride is there, En is there, then counter ion chlorine is there, chloride ion. And understand, whenever you have a counter ion in the question, in the complex given, start from there, start from the counter ion, always keep it in mind. And here the counter ion is chloride, so -1. So to cancel this -1, this complex has to be +1, 1 plus. Clear? Now let cobalt be X, each chloride is -1, En is 0. Then you will equate it to this 1 plus, what you got from the counter ion application. Now write it, it will be X plus, chloride is -1, so -1 into 2 chloride ions are there, plus En is 0, it is equal to 1. So you are getting X minus 2 is equal to 1. So you are getting X is equal to +3. Clear? So the charge on cobalt here is again +3. What will be the name now? The name will be, here you have to call them in alphabetical order, C and then E. Call C first. So how many chloride ions are there? 2. So it is dichlorido, then En coming twice, so it is bis, ethane 1,2-diamine, only one num, take care. So dichlorido bis ethane 1,2-diamine, then cobalt 3. So this is the cation. Cation should be called first, we have called it, and then chloride ion is standing out, so call it as chloride. Cation first, anion second, that's how you name. So what's the name? It is dichlorido bis ethane 1,2-diamine cobalt 3 chloride. Practice such questions well. Now let's take another one. Here you can see platinum is the central metal atom, ammonia is there, chloride is there, nitrite is there. And you can see that full complex, this is the entity. It has no counter ion and no charge bearing also. That means the entity is neutral. Okay, no charge written here. Now let us start. Let us assume platinum as X, ammonia is 0, chloride is -1, NO2 is -1. Let us calculate X plus 0 plus -1 plus -1 minus 2 is equal to 0, because there is nothing written as a superscript. That means it is 0 here. So you are getting X is equal to +2. Platinum is +2. Now what's the name? Call them alphabetically. They are already in the alphabetical order. So it will be diamine, then chlorido. Then here comes the application of ambident ligand, what I told you. NO2 minus is an ambidentate ligand. Here N is written first means it is binding through N. Ligating atom or linking atom is N. So you should call it as nitrito. Why nitrito? NO2 minus is nitrite. Then being an anionic ligand, you have to call it as nitrito. But you have to show the linking atom in an ambidentate ligand. So nitrito N because N is written first. If it is ONO, you will write nitrito O. Then what is the central atom? Platinum. And what is the charge of platinum here? 2. So it is diamine chlorido nitrito N platinum 2. There is no ionic charge here, so don't write ion. If you do that, you will get 0 mark. Clear? It is just a neutral species. Right? Okay. This is also a recent board question. Now we are going to see how to write the formula or structure of a coordination compound or entity from the IUPAC name given. First question, pentaamine nitrito O cobalt 3 chloride. Here what you have to do first is you have to write it like this. What is the central atom mentioned here? Cobalt. So write that first. Pentaamine means you write CONS3 5. Pentaamine. Nitrito O means you will write ONO. If it is written nitrito N, you will write NO2. I have told you that NO2 minus is an ambidentate ligand. It can be nitrito N or nitrito O. Since O is written first, nitrito O, you have to write O first, so it is ONO. Then, so pentaamine nitrito O cobalt 3. So cobalt is in +3 state. Then chloride. Many students stop their work here. They think the formula is correct and they go ahead. Actually, you haven't completed your work. This is not the correct answer. So how to complete your work? What you have to do is, you should know how many counter ions you have to put. Is it Cl1, Cl2, Cl3, what? For that, you have to do a calculation. And what is that calculation? What you have to do? What you have to do? This is 0. This is -1. Okay? So 3 minus 1, it is +2. So that's a charge on the entity. 3 plus 0, 3 minus 1, 2. So if this is 2 plus, there should be 2 minus outside to cancel the +2 charge. Each chloride is -1. So there should be 2 chloride ions to cancel the +2. Therefore, what will be the final answer? It is CONS3 5 times, ONO. Then outside, how many chlorines you have to put? Cl2. This will be the correct answer. Clear? So this calculation you have to do and see how many counter ions. Clear? Okay. Now let's come to the next question. The next one is potassium tetracyanide-nickelate 2. Again, potassium means it is the counter ion. Tetracyanide-nickelate is the complex area where nickel is the central atom. So, nickel, tetracyanide, that means Cn is coming 4 times. So, potassium tetracyanide-nickelate 2. So, that means the complex is negative. That's why it is written nickelate. And nickelate 2, that means, what does it mean? Nickel is in +2 state, right? You know, each cyanide is -1. So, +2 plus -1 into 4, -4, it is -2. That means the charge on the complex is -2. That is why it is called nickelate. Complex is negative. You know, each potassium will be only plus 1. So to cancel the minus 2, there should be 2 potassiums to make it plus 2. Therefore, what will be the correct formula for this one? It will be K2, then NiCN4. This is the correct answer. Clear? Many students lose mark when such questions come in the paper. Most of the students get the IUPAC nomenclature right. That's what we see. But when it comes to writing the formula, many of the students make a mistake in the counter ion part. For you not to happen in that way, make sure to practice them properly. Clear? Okay? Now, next question. Now, let's take the next question. Ammonium tetrafluoridocobaltate 2. Ammonium tetrafluoridocobaltate 2. Ammonium is the counter ion because tetrafluoridocobaltate, that part is the complex. It is very clear. Okay? So, ammonium is the counter ion. It is NH4 plus 1. Now, you know you have to write cation first. So, I put ammonium first, like the last case where you put potassium first. Now, tetrafluoridocobaltate. So, cobalt is the central atom. Tetrafluorido. You don't have to put parenthesis for F because it is a single atom, not a combination of atoms. You know that. Cobaltate 2. That means cobalt is written 2 here. Okay, you have seen cobaltate 2. So 2 means you have to write plus 2 here. Right. Now tetrafluoridocobaltate. This is minus 1. So plus 2 plus minus 1 into 4 minus 4. That means the net result is minus 2. That's the charge on the complex. Clear? Now, to cancel this minus 2, there should be plus 2 charge in the counter ionic part. But one ammonium can have only plus 1. So, there should be 2 ammoniums to make it plus 2. So, what is the formula? NH4 should come twice to cancel the charge on the entity. Clear? It is minus 2, this plus 2. So, this will be the formula of the complex. That is NH4 twice, COF4. It is a textbook question. Practice well. Now, the next question. Potassium trioxalatochromate 3. That's also a textbook question as well as a board question. So, let's see how to do it. Potassium, that is the counter ion, K plus 1. Then, trioxalatochromate. So, chromium is the central atom. Trioxalato, that means oxalate, which is C2O4. Sometimes they may write OX in parenthesis, but when you write, I prefer you writing C2O4 itself. So, trioxalato, so put it twice. So, potassium trioxalatochromate 3. That means chromium is in plus 3 state. That is why it is written chromate 3. And what is the charge on oxalate? You should remember oxalate is minus 2. So plus 3 plus minus 6. Plus 3 plus minus 6. What is that? It is minus 3. So 3 minus is the charge on the entity. So if you have 3 minus here, counter ion should satisfy 3 plus. 1 potassium will be only plus 1. So there should be 3 potassiums to balance the charge. So what is the formula? It will be K3. It will be K3. Then Cr C2O4 thrice. This will be the formula for this complex. Clear? Make sure to practice highly possible questions in your paper, even in 2024. Now, We will do 2 more because I feel you need more practice in this particular area where many students make mistake, as I told you before. Hexa aqua manganese 2 sulfate. Okay. Hexa aqua manganese 2 sulfate. Here sulfate is the counter ion. So this part is the hexa aqua manganese 2 is the positive ion, cation. So start from there, cation first, anion second. Manganese, that is the central atom. Hexa aqua, so it is S2O 6 times. So hexa aqua manganese 2, that means manganese is in +2 state. You know this is 0. So the charge on the entity will be +2. We have discussed these things many times already in this session. Now sulfate. Sulfate is this one. Sulfate is -2. Right? Sulfate charge is -2. So the charge here is +2 and the counter ion charge is -2. They are balancing each other, cancelling each other. Therefore, what will be the formula of this complex? They are already compensated. So the answer will be Mn S2O 6 times sulfate. Here it is not compulsory to put parenthesis because it's coming only one time. I just put it to show the charge, that's all. So if it is coming twice, thrice, etc., you can put parenthesis. Otherwise, you can leave it like this. So this is the answer for this question. Clear? Now let's go to the next question. Iron 3 hexacyanide 3. This question is very common in papers and many students lose mark also in this particular one. Let's see what is the problem in this question. Okay. Iron 3. Iron 3 means it is Fe plus 3. Because you know iron can be in Fe plus 2, that is ferrous form or ferric form. Fe2 plus ferrous or Fe3 plus ferric. Iron 3 means it is Fe3 plus. Clear? Now, that is the counter ion. Now come to the complex area. Hexacyanide. Ferrate means again iron is the central atom. Ferrate means that the area is, complex entity is negative. That's why it is coming 8. Ferrate. This is cation, complex is negative. Now hexacyanide. So hexacyanide ferrate 3. Ferrate 3 means what? Again iron is plus 3 here. That is why it is written ferrate 3. Cyanide is -1. So what is the net result here? Plus 3 plus -6. So the net result is -3, right? So the net result here on the complex charge is -3. Here it is plus 3. So plus 3 and -3, they cancel each other. Means this 3 will come here, this 3 will come here, they cancel each other. So you have to write Fe, then FeCN6. Clear everyone? So it is this 3 plus and this 3 minus, they cancel each other and you are getting FeCN6. This is the answer for this question. But let me innovate this question, which is also a board application. Okay, application question. It is there in some papers. I'm just going to make a small change here. Suppose, that's also a board question, come on. Here also, we can make it Fe2. Okay, that is iron 2 hexacyanide ferrate 3. Suppose they give it like this in the paper. What will you do? Here then it is plus 2, right? Iron 2. Now this part is saying hexacyanide ferrate 3. So now this is 3 minus, this is 2 plus. What will you do? Do they cancel out? No. So what you have to do? You have to exchange these oxidation states. That is, this 3 will come here and this 2 will come here. So what will be the formula of this complex? It will be Fe3, FeCN6 twice. See? Formula changed. I just made a small change in this area. The answer changed completely. Understand? So this is where students lose mark when you get such questions involving iron, outer and inner part. Okay? Practice well. be more careful when you do such questions in the board paper. Okay. Next one, tetraamine diaqua cobalt 3 chloride. Let's see what it is. You can see tetraamine diaqua cobalt 3 chloride. So this is the cation, this is the anion. So tetraamine diaqua cobalt. Cobalt is the central atom. Tetraamine. You have to write here also in the alphabetical order. It's already given the alphabetical order, so no problem. AM before AQ. Okay? If the first letter is same, see the point of difference. Here the second letter is different. So whatever is coming first, you select that. So already in that order itself. Tetraamine diaqua. Diaqua. Then, so tetraamine diaqua cobalt 3 chloride. Now, cobalt 3. Cobalt 3 means it is in plus 3 state. Cobalt 3. This is 0. This is 0. So, the charge on the complex is plus 3. Charge on the entity is plus 3. As I told you before, one chloride will be only minus 1. To cancel plus 3, there should be minus 3. So, there should be 3 chloride ions. And the formula will be CO, NS3 4 times, then H2O 2 times, and then Cl3. This is the answer. Yeah? Board question. You can see it is 2019 board question. Now the next one. Dibromido bis ethane 1,2-diamine platinum 4 nitrate. You can see nitrate is the counter ion. So this part is the cation. So cation first, anion second. Now what is it? Platinum 4 nitrate. Platinum is the central atom. Dibromido. So Br 2 times. Then bis ethane 1,2-diamine means En 2 times. So dibromido bis ethane 1,2-diamine platinum 4. Platinum 4 means platinum is plus 4. Nitrate. Nitrate is minus 1. Now let us see how many counter ions should come here. Check. Here Br is minus 1, En is 0. So what is the charge on the entity? 4 plus minus 2. So you are getting plus 2. Right. Plus 2 is the charge. 4 minus 2 plus 2 is the charge on the entity. So each nitrate is minus 1 only. There should be 2 nitrates to cancel the plus 2. Plus 2 should be cancelled by minus 2. So there should be 2 nitrates. That is the final formula. So what is the answer? PT. For Br2, no parenthesis required. Okay. Then En twice. Then it is NO3. Here parenthesis is required because it is coming 2 times. If it is only 1 time, no parenthesis required. So the correct answer is PT, Br2, En twice, NO3 twice. Clear? I hope you got enough practice on how to write the formula or structure from the given IUPAC name. Practice very well. It is very, very important. Next topic is isomerism. So we are going to see what are the different types of isomerisms shown by coordination compounds. Okay. Let's see what are the different types of isomerisms shown by coordination compounds. Isomerism in coordination compounds classified mainly into 2 as usual. Structural isomerism and stereoisomerism. What is structural isomerism? You have done these things already in class 11 chemistry, organic chemistry area also. More or less the same thing. Structural isomerism. Structural isomers have the same chemical formula. You know, isomers, they have the same chemical formula. But structural isomers, they have different bonds. When you come to the coordination compounds, different structural isomers of coordination compounds, they have same formula but different bonds. And what are the different types of structural isomerisms seen in coordination compounds? There are 4 of them: linkage isomerism, coordination isomerism, ionization isomerism, and solvate isomerism. We are going to see what these are in detail. And when you come to stereoisomerism, there are two types of stereoisomerism. That is the geometrical isomerism and optical isomerism. Then we will be dealing with them in detail here. Now, what is meant by linkage isomerism? It is normally seen in those complexes which have ambidentate ligands. I have told you nitrite NO2 minus is an ambidentate ligand. It can ligate through N or O. Then we will call it as nitrito N, nitrito O. They have different properties. You can see here, this one is pentaamine nitrito N, cobalt 3 chloride, right? 3 minus 1 is 2. So it is outside counter ion 2. So pentaamine nitrito N, cobalt 3 chloride. So this is nitrito N. Look at this. It is exactly same except for the linkage in NO2. Here it is ONO. Otherwise everything same. Everything else same, right? So these two complexes, they are called linkage isomers because they have the same formula overall and they have different linking atoms in the ambidentate ligand. So this type of isomerism arises in a coordination compound containing ambidentate ligand. Very important definitions. Learn all these definitions well with one example for each. That is always better. Instead of giving the definition alone, you give one example to support the definition also. That will help you in scoring. Clear? Okay. Now, what is the next one? The next one is coordination isomerism. Where is coordination isomerism seen? When both the cationic and the anionic entities are, anionic species are complexes. That is, cationic entity is a complex entity and anionic area is also a complex entity. When such coordination compounds are seen, there we can think about coordination isomerism. Clear? And how you create this coordination isomerism, how you make a coordination isomer? It arises from the interchange of ligands. You can see we are interchanging the ligands, but we are going to apply little more in detail here. It is written this is the definition given in your textbook. Interchange of ligands. That means if you are simply interchanging the ligands, Cn will come here and NS3 will come here. What will happen then? You are getting CO, CN6 and CrNS36. This is what happens if you simply interchange the ligands. Definition goes like that, interchange the ligands. But after interchanging the ligands, the problem here is, now this is the cation, chromium is 3, this is 0, so 3. And here cobalt is 3 plus minus 6, this is minus 3. So do you think you can present a compound like this? Always cation first, anion second. So even if you exchange the ligands, you have to do one more thing. What is that? Again, bring the cation first, anion second. Then only we can present it as the correct formula of the compound. So you can see if cation is brought first, you will get CrNS3 6 times first, then anion second, you are getting this. So even though the definition goes, you can't change the definition, right? Interchange of ligands, okay. But when you do it in the paper, what will you do if you want to create the coordination isomer? Let the ligands be there. You just switch the metal ions. See? Chromium you put here and cobalt you put here. You get the isomer directly. Instead of exchanging the ligands, then again rearranging cation first, anion second, straight away switch the positions of the metal ions. You will get the answer. But when you define, you have to go by the standard definition itself. You can't change the definition. Clear? Right. Now, the next one, ionization isomerism. What is ionization isomerism in coordination compounds? Let's see when it arises. Look at these two complexes. CONS3 5 times SO4 Br. CONS3 5 times Br SO4. What happened here? If you look at this, overall formula is same. Same group, same metal, everything same. Number also same. How many times they are repeated. But the only change is, if you want to change this into this, you pull Br in and you put the sulfate out. Clear? That's what we have done. That means, when here counter ion is bromide ion, sulfate was a ligand. So here, counter ion, which is standing outside the entity, it is a species which can act as a potential ligand. So, pull the counter ion inside and push the ligand out as the counter ion. It is the mutual exchange between counter ion and the anionic ligand. Normally it happens between the anions. So, Br minus is pulled in, SO4 2 minus is pushed out. You get this. That is the ionization isomer of the first one. And why they are called, and one more thing, don't think that the charges will get affected. No, they will get internally compensated. You don't have to worry about that at all. When Br minus is pulled in and SO4 is pushed out, charges will get balanced externally and internally. Okay, when you calculate, you can see. Now, why they are called ionization isomers? If you put this in water, what will happen? It will produce bromide ion and this ionic entity, coordination entity, different ions. But if you put this in water, it will produce sulfate ion and this one. So, like what I told you in the very beginning, complexes, they don't ionize completely. They ionize into the ionic entity and the counter ion. Here, it will produce Br minus ion and CONS3 5 times sulfate plus. Okay? That means Br minus ions will be present in solution. But sulfate ions will not be present in solution because that is inside the square bracket, inside the entity. It is not ionizable. Clear? So this solution will answer the test for bromide. When you add dilute HNO3 followed by silver nitrate, you will get pale yellow precipitate of silver bromide. Okay? But when you come to this one, Br is inside the entity, so Br will not be present in the outside solution. Okay, it's not a counter ion, it's not ionizable, but sulfate will be present outside. So do you think you will get a pale yellow PPT when you add HNO3 and silver nitrate? No, because Br minus is inside, it is not there in the solution. So they produce different ions. This will produce sulfate ion and this complex ion. Okay, different ions are produced by ionization isomers in solution. That's why they are called ionization isomers, and the phenomenon is known as ionization isomerism. Clear? Now, so the definition is very important. It arises when the counter ion in a complex salt, see, counter ion in a complex salt is a potential ligand, and it can displace a ligand which can then becomes the counter ion. That is, counter ion becomes the ligand and ligand becomes the counter ion. That's what is happening in this case. Clear? Now, next one, solvate isomerism. As the name indicates, solvate means it is related to solvent. It is also known as hydrate isomerism if water is the solvent, hydrate isomerism. And let us see what is causing this solvate isomerism when water is the ligand, for example. Solvate isomers differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecules in the crystal lattice. And it is similar to ionization isomerism. I have given their original colors here. This is hexa-aqua-chromium 3 chloride. Here all the water molecules are inside the entity acting as ligands. Right? All solvent water molecules are inside. And this complex is violet in color. Whereas here, one water molecule is pushed outside. You can see out of 6, one water molecule is pushed outside. That place is taken by one chloride ion which is pulled inside. So it becomes Cr H2O 5 times Cl. Then out of Cl3, now only 2 Cls are outside, one is pulled inside. So Cl2 dot, that one water molecule which came outside, it is acting as water of crystallization. Now here all are ligands, all water molecules, but here only 5 water molecules are acting as ligand. One is outside in the crystal as water of crystallization. Clear? So we will say these two are mutually what? Hydrate isomers, or generally solvate isomers. Clear? It is also important for application question in the paper. Understand? Let us do the IUPAC nomenclature also for such complexes for a practice. Okay? What is this? This will be hexa aqua. Chromium you will be getting 3 when you calculate. So chromium 3 chloride. Hexa aqua chromium 3 chloride. What about this? How will you name such a complex when water is standing outside in the crystal lattice? This is penta aqua chlorido chromium 3 chloride hydrate. If there is water molecule outside the square bracket, you have to call it as hydrate. It is water of hydration or water of crystallization. If it is 2H2O, you will call it as dihydrate. If it is 3H2O, you will call it as trihydrate. Got it? So that is how you have to, and it is a common question nowadays in board papers. They will give you such questions for nomenclature. You should know how to do it. Clear? Okay. Now moving on to stereoisomerism. Let's see what is stereoisomerism. Stereoisomers have same chemical formula. Just like structural isomers, they also have the same chemical formula. Same chemical bonds, then different spatial arrangement. So what all are same? They have the same chemical formula, same chemical bonds also. In structural isomers, chemical bonds were different. Here bonds are also same. Same formula, same bonds. But there is difference in the spatial arrangement. Arrangement of groups around the central atom or ion. That arrangement is different. That gives rise to stereoisomerism. Clear? Now, what are the two types of stereoisomerisms? Geometrical isomerism and optical isomerism. In class 11, in coordination, in organic chemistry, you have studied cis-trans isomerism in organic compounds. That was the geometrical isomerism, what you have learned. Now, you will be dealing with some more types of geometrical isomerisms. Okay? In addition to cis-trans, we will be doing one more in coordination compounds. And then second one is optical isomerism. So we are going to do them in detail one by one. Geometrical isomerism. What is geometrical isomerism? It is shown by heteroleptic complexes where the ligands are different. Okay, complex homoleptic and heteroleptic we have discussed already in the same session. So where ligands are different. So it is shown by heteroleptic complexes, cannot be shown by homoleptic complexes because arrangement will be same with respect to each other, whichever way you see. So it is shown by heteroleptic complexes due to different possible geometrical arrangement of the ligands. So when you have a heteroleptic complex, there will be different ligands and they can be arranged differently in different geometrical isomers. Then we are going to discuss geometrical isomerism under two headings with coordination number 4 and coordination number 6. Let's take coordination number 4. If coordination number is 4, there can be two types of complexes. One is square planar, the other one is tetrahedral. What is the shape of square planar? Square planar means if this is the central metal atom, then this is square planar geometry, right? When you join, you will get a square. And what is tetrahedral geometry? If this is M, it will be like this, okay? Here, these are the ligands. Here, these are the ligands. So, this is the difference in geometry of coordination number 4 square planar, coordination number 4 tetrahedral. So, square planar complexes of the type M, X2, L2. That means two of them same, then next one, X and X. So MX2, L2 type, they can show geometrical isomerism. They can show cis-trans isomerism. But if you have a tetrahedral complex, then, if the ligands are all same, there is no chance of geometrical isomerism. If the ligands are different, then also, if it is tetrahedral geometry, it will not normally show geometrical isomerism. Why? If you look at in 3D format, what will happen? The relative positions of these ligands with respect to each other will be same. That means they will not show geometrical isomerism. It is a repeated board question. It is a solved example in your textbook. Please do prepare it. Okay. So, square planar complexes of the type MX2, L2, where X and L are unidentate ligands, they can show this type of isomerism. And that is called cis-trans isomerism here. That type of geometrical isomerism is cis-trans isomerism. Now, let us take the example PTNS3 twice Cl2. What is the name of this complex? Let us revise nomenclature. It is diamine dichlorido platinum 2. Why? Because if you look at the charge, here this is X, 0, and this is minus 1. Overall it is 0. So X plus minus 2 is equal to 0. You are getting X is equal to plus 2. That means what is the name of this complex? Diamine dichlorido platinum 2. No ion because it is not in ionic state. Clear? Now, it is MX2L2 type, where all of them are unidentate. Let's see what are the geometrical isomers of this complex, cis and trans. What is cis isomer? Similar groups on same side cis, similar groups on opposite sides it is trans. You have studied it even in class 11. So, PT, Cl on same side. Ammonia on same side. This is the cis isomer of this. And what is the trans isomer? Again, draw square planar. Cl opposite. Ammonia. You should connect it with ammonia because nitrogen is the donor atom. So write ammonia in that way. And this one. So this is trans isomer. This is cisplatin, which we did in the beginning. Intro area, cisplatin is used in cancer therapy. So this is that chemical. Okay, cisplatin, and this is transplatin. Clear? So these are the two geometrical isomers. This is the trans isomer, and this one is the cis isomer. They are the geometrical isomers of this compound. Ma2B2 or X2L2 with coordination number 4. Clear? Now, this I have already told you. It is very, very, very important. Commonly asked question, solved example. Tetrahedral complexes having two different types of unidentate ligands. Same MX2, L2 type or A2B2 type. Two different types of unidentate ligands, but shape is tetrahedral. Then they will not show geometrical isomerism. Why? Because the relative positions, in 3D format, position with respect to each other, that's called relative position, of the unidentate ligands attached to the central metal atom are the same with respect to each other. When relative positions are same with respect to each other, there is no difference in arrangement from whichever direction you see. That means there is no geometrical isomerism in tetrahedral complexes. Okay? Then square planar complexes of the type MABCD. MABCD means 1, 2, 3, 4. 4 different ligands. All the 4 are completely different and they are unidentate ligands. And if the shape is square planar, it can show 3 geometrical isomers. Okay? There is a question in the exercise. PT, NS3, BR, CL, PY. A, B, C, D. We can arrange these groups in 3 different ways. You can refer to the exercise question. You get 3 isomers. Okay? You can fix one of them at one corner and change the others. Then you will get 3 different isomers. Okay? And there is a question along with that, which one of them is chiral? Actually, none of them is chiral. Understand? All of them are achiral. Clear? So you have to practice that question. It is also a commonly asked board question. Exercise question it is. Now, let's come to coordination number 6. When you come to coordination number 6, there are two different types of geometrical isomerisms possible. One is cis-trans, the other one is facial meridional. So we are going to see what are they and when they are exhibited. Come to this type, MX2L4 type, where both X and L are unidentate ligands. So X ligand is repeated twice, L ligand is repeated 4 times. Because they are all unidentate, 2 plus 4, 6 is the coordination number, right? Now, let's see how to draw the cis and trans isomers of this complex. Easy. You can use this trick. Easy to remember. If coordination number is 6, think about octahedral geometry, right? Now, you just look at the formula given. Which ligand is repeated twice? Take a note of that ligand. And we are going to use that ligand for creating cis and trans easily. Here X is coming 2 times. So you put X here and here. That means one equatorial position and one axial position, adjacent positions. You put them as X. So this is, X2 completed. Remaining ones you can put L. So this will be the cis isomer of this particular complex. And how to make it trans? Do the same thing. Draw octahedral geometry. Now X is repeated twice, catch hold of that and put X here, opposite, and remaining L here. So when X and X are like this, it is cis, adjacent positions. When X and X are opposite, it is called trans. So this is the trans isomer. You have to register this properly. It is very, very important. They will not ask you a question in general format. They will give you a specific question and ask you to draw the cis and trans isomers of that complex. So you have to see what is the coordination number and do it accordingly. Okay? We can see one question here. This is a board question. It is there in the textbook also. You have to draw the cis and trans isomers. Means the geometry, might not say cis and trans. They will say you have to draw the geometrical isomers of this particular complex. How to do it? What is the trick what I told you? It is M A4B2 or A2B4, whatever. So this is repeated twice. Just catch hold of what is repeated twice. I told you. Then what you have to do? M. What is the central atom? M. That is cobalt here. Then draw the octahedral geometry. Then what did I tell you? Here chlorine is repeated twice. So put one here, one here. All others are ammonia, which is repeated 4 times. And when you draw ammonia, it is better to take care that you are connecting the nitrogen of ammonia to the central atom, because nitrogen is the donor atom, which is donating the electron pair through dative bond. Clear? Okay, so, and here you can put a corner bracket. Instead of putting the entire thing in square bracket, you can use a corner bracket and put plus here, meaning is the same. Okay? What is trans now? Do the same geometry. Octahedral. Now, repeated twice is chlorine. So put chlorine here, opposite. Then NS3, 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 NS3. This will be the trans isomer. Clear? So here you will write, this is cis, then write the formula. CO, NS3 4 times, then Cl2. This is cis isomer. Similarly, this one will be trans hyphen. Then you write the formula of the complex. That's what you have to do. Clear? Right. Now, let's see this complex. It is also from the textbook. I selected these 2 questions because same thing is repeatedly asked. Both these questions are repeatedly asked in many board papers. So I selected those two same questions. Okay. So let us see how to do this. Here, what is the central atom? Fe. You can see Ma2B4 again. So draw the 6 bonds. Then what is repeated twice here? Ammonia. So one ammonia here, one ammonia here. One ammonia at the axial and one at equatorial position. All others are cyanide. And it will be Cn. Then corner bracket minus. So this is the cis isomer. How will you write? Cis hyphen. Then you write Fe, NS3 twice CN4. You will write that. Cis hyphen, then write that formula. Then what is the trans isomer? Fe. Now what is repeated twice? Ammonia. Put them opposite. And then cyanide, 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 and cyanide. This is the trans isomer. You will write trans hyphen that formula. Clear? It is also repeatedly asked. Please do practice. Then, so we have discussed one type of geometrical isomerism, cis-trans isomerism, in complexes of the type MX2L4. Okay? That is two types of unidentate ligands, but one is repeated twice, one is repeated 4 times. Next variety is same coordination number 6 only, but it is MX2. What is the meaning of this LL2? LL2 means there is a didentate ligand. It is not L2. It is LL2. That means there is a didentate ligand. So what is the coordination number here? LL means it's a didentate ligand. So 2 into 2, 4 plus 2, 6 only. Coordination number 6. But there is a didentate ligand. In MX2L4, all were unidentate. Understand the difference. Now, how to draw their cis and trans isomers? So these are having didentate ligands, which is indicated by LL. I'm going to show you through this example how to do it. Simple. You take cobalt, then draw the 6 bonds because coordination number is 6. Now, one is chlorine, one is En. Both are repeated twice. Now, what we can do, chlorine on same side, En on same side. Then this will be the cis isomer. Do you get me? That means similar groups on same side. That is cis. Cl, Cl same side, En, En same side. That will be cis, COCl2, En2 plus. You have to write it here fully. Okay, I'm not writing it, but you have to write it fully. Then what is trans? Trans means you draw the same thing again. Then Cl, Cl opposite. En, En opposite. Then this is the trans isomer. So these are the cis and trans isomers, geometrical isomers, when it is MX2 LL2 type with coordination number 6. And later you will study in the same optical isomerism, in this session only when we continue, you will study this will show optical isomerism, because when you take its mirror image, this will not be superimposable on the mirror image. So the cis isomer can show optical isomerism, whereas this one, if you rotate it through 180 degree, the same thing will be produced 180 degree, and they are superimposable. This is superimposable on its mirror image. It will not show optical isomerism. Anyway, we are coming to that point shortly. Okay. Now, next one is A3B3 type, where all A and B are unidentate. This is where the facial meridional isomerism comes into picture. Okay, let's see how it is explained. Here, how you draw the facial and meridional isomers. That's also a type of geometrical isomerism of this type, Ma3B3. Look here, M. You draw the 6 bonds. Now, either NS3 or NO2, anyone you can take because both are repeated thrice. I'm going to show with the NO2 here. So, facial means what? You will put NO2 here, NO2 here, NO2 here. Then NS3 here, NS3 here, NS3 here. Understand? It can be opposite also. Okay? NS3 is here, NO2 here, whatever. Now, you know why it is called facial. I'm just going to complete the base of this octahedron, and then I'm going to complete one face of the octahedron. Look here. This is one face of the octahedron, right? Okay? So if you take this NS2, then one face of the octahedron is occupied by, this is one face of the octahedron. It is occupied by NO2. You can see. That is why it is called facial isomer. This is one face of the octahedron occupied by NO2. Similarly, if you join this here also, you can get one face. You can see here. I'm going to connect it like this. See? This is also one face of the octahedron. So this is also one facial area. So this is one facial area. This is one facial area. So such an isomer is called facial isomer of Ma3B3 type. Clear? Now what is this meridional isomer? Let us see what is this meridional isomer. Look here. Meridional isomer means you write the same thing. Okay? Then I have put the 6 bonds. Meridional space, see, this is the base of the square in the square bipyramidal octahedral state. Now, any one half of the base, this is called the meridional space. Okay? So, I'm going to put NO2, then NO2, and NO2. I told you I'm drawing with respect to NO2. I'm going to shade this area, meridional area. Okay? So this is NO2, NO2, NO2. This is called meridional isomer. Automatically, the other 3 areas will be occupied by ammonia. So these are the 2 geometrical isomers of the type Ma3B3. This is facial isomer. This is meridional isomer. Clear? So these are the 2 different geometrical isomerisms. Cis-trans, which is in Ma2B4 or X2L4 or X2LL2. Cis-trans. Ma3B3 or X3L3, whatever. Then it is what? Facial meridional isomers. Clear? Practice these drawings also. They are important. Now, coming to optical isomerism. You know optical activity you have done in haloalkanes, haloarenes. I have myself explained in my previous sessions. What are enantiomers? They are optical isomers. One is dextrorotatory, the other one is levorotatory. They are non-superimposable mirror images. They are called enantiomers. They have optical activity. Same thing here. Optical isomerism, when you apply it into coordination compounds, optical isomerism is common in octahedral complexes where coordination number is 6, involving 3 didentate ligands. Okay? Then optical isomerism is very common in them because they have no symmetry. If there is no symmetry, they can show optical isomerism. If there is an element of symmetry, cannot show optical isomerism. So they have no symmetry and they are non-superimposable on their mirror images. That is why they are able to show optical isomerism. Means coordination number 6 with 3 didentate ligands, they will show optical isomerism. Due to these 2 reasons, no symmetry, they are non-superimposable on their mirror images. Now look at this example. You can see CO-En thrice. Here En is the ligand. It is a didentate ligand repeated 3 times. So it can show optical isomerism. Optical isomers are shown in your textbook. Please do practice. I will just show you what are the structures quickly. You know, CO, draw the 6 bonds. Now I am going to put three ENs, 3 didentate ligands. Suppose it is EN here, EN here, EN here, and it is 3+. If this is dextro, its mirror image will be levo. What will be its mirror image? CO. Then here I put 2 left, 1 right. Let me put 2 right and 1 left. This will be its mirror image. So if one is dextro, the other one is rotated through 180 degrees, so it will be levo. Okay. So if you try to make it come on top of this, 1 EN will come on top of 2 ENs. These 2 ENs will come top of 1 EN, not superimposable. So they are non-superimposable mirror images and they can show optical isomerism. Clear? Okay. Now, this I have already discussed when we did geometrical isomerism, but let's repeat. Out of the following two, this is a repeated board question. Out of the following 2 coordination entities, which one is chiral? Chiral means optically active. This is cis, this is trans. What is cis? Structure. Let us draw the structure. It is CR. You can see it is X2, oxalate is LL, didentate. So coordination number is 6. So let me draw. It is CL, OX, OX. This is the cis isomer. If you take its mirror image, what is it? CO. Then rotate it through 180 degree. CL, OX, OX. 3 minus. Just check. If you pull this on top of this, OX will come on top of CL will come on top of OX. They are not superimposable. So this is not superimposable on its mirror image. If one is dextro, the other one will be levo. That you have to do the optical projection and find out. Optical activity experiment. So this is not superimposable on this mirror image. So cis isomer, since it is not superimposable on its mirror image, it is optically active. But if you take trans, what will happen? What is trans? You can see what is the trans isomer. We can see whether it is superimposable on its mirror image. Let us find out. What is the trans isomer? CR. Then trans means CL, OX, OX. Similar groups on opposite side. This is the trans isomer. Now, mirror plane. Then what is its mirror image? It will be the same thing, right? Because this OX will come at the right side, but it's OX only. This OX will come on the left side. It is again OX only. CL. So this is its mirror image. Just check. If you pull this on top of this, OX will come on top of OX. This OX will come on top of OX. CL will come on top of CL. This CL also will come on top of CL. 100% superimposable. That means it is optically inactive. So trans isomer cannot show optical activity. So there is no optical isomerism where it is superimposable on its mirror image. Okay, so it cannot show optical isomerism. And cis isomer, yes, it can show optical isomers. Clear? You have to prepare it very well. It is compulsory to be prepared. It is highly expected even in your board paper. Okay? Please make sure to prepare. Now, you can come to this knot point. These are extra information which you can keep in your mind if you want to do application questions. Square planar complexes generally do not show optical isomerism. That is optical, this I stands for isomerism, okay? Square planar complexes generally do not show optical isomerism because they possess element of symmetry. I have already told you. They can show some cases, they can show you optical isomerism only when they have unsymmetrical chelating ligands. But that is, they are not there in your syllabus. Just mention, that's all, for competitive examination purpose. Clear? Now we are coming to an application question from this area, which is commonly seen in the board papers. 3 geometrical isomers are possible for CO, En, H2O twice, NS3 twice. You know, they are not in the alphabetical order, but you don't have to question the question. Let it be. This is how it is given in the paper. Draw the structures of these 3 isomers and indicate which one of them is chiral. And when you get such a question, students have a difficulty in finding out what are the isomers and how to draw them and all. So make sure to practice this question, highly expected even in forthcoming papers in forthcoming years. So in the first one, what I have done is I made 2 ammonias mutually cis, 2 water also cis. But En, it is placed here, okay? Between 2 equatorial positions, En is placed. Here, I put 2 ammonias trans, but 2 ammonia cis, En at the same place. Third one we can try in this way. Here, ammonia, ammonia cis, water, water also cis, adjacent. But En, I changed the position. It is between 1 equatorial and 1 axial position. So however you arrange, these are the only possibilities what you arrive at. Clear? So you are getting 3 different possibilities. These are the 3 different geometrical isomers. And they have asked you which one of them is chiral. Actually, all of them are chiral because all of them are non-superimposable on their mirror images. Clear? That's the answer. Now, that's all about the isomerism area. The next topic what we are going to do is valence bond theory, that is bonding in coordination compounds. There are 2 theories what we are going to discuss. First one is valence bond theory and next one is crystal field theory. So next topic is valence bond theory. Okay? Now going to bonding in coordination compounds. 2 theories of bonding in coordination compounds we are going to learn. That is first one valence bond theory, second one crystal field theory, CFT. What is valence bond theory? I have mentioned about inner orbital complex, outer orbital complex, etc. in the beginning when we discussed the definitions. So, according to this theory, the metal atom or ion under the influence of ligands, means when ligands approach them, what happens? They will use their N-1D, means inner D, NS and NP, outer S and outer P, or NS, NP, ND, outer S, outer P, outer D, orbitals for hybridization, to yield a set of equivalent orbitals of same energy, you know that, and having definite geometry. If it is N-1D, NS, NP, that is N-1D, NS, NP, then it is like D2sp3 or DSP2, like that, inner orbital complex. Okay? Normally we use that term in octahedral coordination. That is N-1D, NS, NP, or NS, NP, ND, outer S, outer P, outer D. Such ones will result in outer orbital complex. When we detail them in the forthcoming questions, you will understand it better. Okay? Now, there are some limitations also for valence bond theory. Actually, there are 6 points of limitations of VBT. And can you imagine, it was asked in 1 year for 3 marks without choice. That means you have to write all the 6 points, half mark for each. That was the marking scheme that year. Okay? So, make sure to prepare limitations of valence bond theory also from the textbook. Okay? Now, we are going to do some examples, how to explain this based on valence bond theory. They will ask you to explain the hybridization, shape, magnetic nature, etc. of the following complexes. That's how you get it in the paper, and they will give you the atomic number of the atom involved, central atom involved. Okay? Now, let us do some samples. So, let us find out what is the hybridization in this complex. What is its magnetic nature, paramagnetic or diamagnetic, highly paramagnetic, weakly paramagnetic, etc. And what's the shape? Let's see how to proceed in such questions. First of all, you calculate X. What is the oxidation number of the central metal atom? X plus 0 is equal to plus 3. So you'll be getting X is equal to plus 3 here, right? X plus 0 is 3. Just like how you have done in nomenclature area. Now, cobalt will be given as 27 in the paper. It is better to know the atomic numbers of the 3D series to be on the safer side, but mostly they will give the atomic number in the paper from coordination compounds. So, cobalt 27 is what? Argon 18, 3D 7, 4s2. This is cobalt 27. But here cobalt is 3 plus. So what is cobalt 3 plus? Here it is argon 18. 2 electrons are lost from here, 1 more from here. So it will be 3d6. So 4s is there, it is empty now. 4p also will be there, it is empty. If required, we will use it. Let's see. Okay. You can see it is having coordination number 6. That is octahedral coordination. So the hybridization can be, remember like this, can be only D2sp3 or sp3d2. Only these two. Okay. Now, let us draw it. It is 3d6. 1, 2, 3, 4, 5, 6. Then 4s and 4p. This is the situation in the cobalt 3 plus ion. Now look at the ligand. Ammonia. You know, ammonia is a strong ligand and it can force pairing, right? It will force pairing. Moreover, you can think like this in valence bond theory, that you need 6 orbitals to have 6 hybrids. Because coordination number is 6, you need 6 hybrids to bond with the 6 ammonias. So to get 6, you have to mix 6, right? So let us see how to, if you take this, 1, 2, 3, 4, then 5 and 6 you have to take from the outer D. But ammonia is a strong ligand. It can force pairing in the inner D. So what happens here is, this one can come here and this one can come here, vacating these 2 orbitals. So these 2 inner Ds become free. Now what will happen? 1, 2, 3, 4, 5, 6. These 6 can be mixed and the hybridization can be D2sp3. Now check. We are using 3D, N-1D, NS, NP. So it becomes inner orbital complex because inner D is involved in hybridization. Clear? Now, such a complex is also called, this inner orbital complex is also called, you can see here all electrons are paired. So it is called spin paired complex. Or there is no unpaired electron here, means it will be low spin complex. So there are 3 names for this. One is inner orbital complex or spin paired complex or low spin complex. Clear? Now let's go ahead. If hybridization is D2sp3, what will happen? It will become octahedral in shape. Actually, you have to explain it like this in the paper if it is for more marks. How you have to do is, after, see, they got paired and now this is 3D only. It has become 6. Okay, 3 pairs. Now the 2 Ds and 1, the 2 Ds, that is 3D, 2 of them, then 4s and 4p. All of them are mixed together to get 6 hybrids, right? You can see they are mixed to get 6 hybrids. See, 1, 2, see, these 3 are now existing together. Now 1, 2, 3, 4, 5, 6. These 6 will become 6 hybrids. That is what I have shown here. These 3 are together, the inner D with their orbitals, and these are the 6 hybrids. Now, the ligands will be donating their electron pairs into these hybrid orbitals. So, how can you draw them? One pair of electron coming from one ammonia ligand, next pair of electron coming from next ammonia ligand. Like that, 6 pairs of electrons can be given by 6 ammonia ligands. So this is the situation in that particular complex, CONS3 6 times 3 plus. Now coming to magnetic nature, you can see in the inner Ds, you can see here, there are no unpaired electrons. So the complex will be diamagnetic. So coming to the points, value points for such questions in the board paper, hybridization they will ask you, that is D2sp3. Then it is diamagnetic due to the absence of unpaired electrons. And what about the stereochemistry? Means shape of the complex. If it is coordination number 6, it will be definitely octahedral. And in this particular case, I will show you that shape also being the first example of its kind. So CO, how to draw it? CO, NS3, 6 times. Being octahedral, you will draw it like this. NS3, NS3, then 3 plus. So this is the shape of that complex, octahedral. Clear? Now, coming to the next question, COF6 3 minus. How this will change? Only one difference. Beginning parts all same. Because here also cobalt is 3 plus. Like in the previous case, cobalt 3 plus will be argon. Same thing like in the previous question, so I'm not repeating. Argon 18 and it is 3d6. Alright. So it is 3d6 means 1, 2, 3, 4, 5 and 6. Right? Now this is 3d. 4s is empty. 4p is also empty. So 4s, 4p. Right. Now here there is a problem again. Because coordination number is still, so you will need 6 hybrids. But fluoride ion which is used here, it is a weak ligand. It will not force pairing. That means these electrons will not be pushed inside. So the inner d orbitals cannot be vacated. So what is the only possible way? You have to take here no help from the inner d. So 1, 2, 3, 4. Remaining you have to take from the outer d itself, from 4d. That is 1, 2, 3, 4, 5, 6. So it will become sp3d2 hybridization. And this is called outer orbital complex. Why? Because we are using 4s, 4p, 4d. Outer d is used, unlike the previous one where you used 3d, which is inner d. So this is outer orbital complex. Now what will be the next figure? It will be this side, no change. 1, 2, 3, 4, 5, 6. So now these 6 will become 6 hybrids. 1, 2, 3, 4, 5, 6. These are the 6 hybrids. And these 3 d orbitals, remainder, they are not used for hybridization. So this is inner d. Then 6 hybrids using all this 1, 2, 3, 4, 5, 6. And then so 1, 2, 3, 4, 5, 6. These are the 6 hybrids and these are the 3 Ds which are not used for hybridization. Now, next step, there will be 6 pairs of electrons coming from 6 fluoride ion ligands and they will make the bonds. Clear? Now, coming to the stereochemistry, this also will be coordination number 6 means it will be octahedral. That is CO, F, 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 all will be fluoride ions. F you have to connect. And then you have to come to the magnetic behavior. So here what is happening? Here there are 4 unpaired electrons in the inner D, making it highly paramagnetic. And because it is sp3d2 or d2sp3, hybridization means it is octahedral and or spire bipyramidal geometry. And this is outer orbital complex. Clear? And if you want to draw the shape, then you can do in the same way what we have done before. That is, you will draw CO, like this. All these will be fluoride ions. So you can put F. Fluoride ions giving their electrons to the central cobalt, and it will be 3 minus. This will be the shape. Clear? Now, so such questions are very common in your papers. Make sure to practice them. Now, this is a board question. They have asked hexa aqua iron 3 ion. It is strongly paramagnetic. What is the meaning of it being strongly paramagnetic? Paramagnetism is due to the presence of unpaired electrons. Strongly paramagnetic means large number of unpaired electrons. So keep that in mind and try to answer. And iron's atomic number is given 26. Okay, let's find out. Iron is 26. What is the configuration? Argon 18, 3d6, 4s2. This is Fe. Here it is Fe3 plus because x plus 0 is 3. So it is Fe3 plus. And it will be argon 18 and 3d5. 2 electrons from here, 1 more from here. 3d5. Now, I will give you the basic idea. Here it is 3d5. Right. Now, there is 4s and 4p. All of them are empty. Right? Now, we have to think whether it is inner orbital or outer orbital. Water is an example for a weak field ligand. Okay? So, it will not force pairing. It is a weak ligand, so it will not force pairing. That means no help from here. So, sp3. Now, you have to take. So, it is. Now, this is 4s, 4p, and then 4d. Now, here 1, 2, 3, 4, 5, 6. So, it will be sp3d2. That will be the hybridization. Hope you understood it. It's similar to what we have done in COF63 minus. Remaining drawing, I'm not going there. So, here, see how many unpaired electrons are there? 5 unpaired electrons. So, it is highly paramagnetic. You have studied in D and F block how to calculate the magnetic moment. Mu is equal to square root of n into n plus 2. Okay? Spin only formula. The more the number of n, more the paramagnetism, more the magnetic moment. So, this has maximum paramagnetism because it has 5 unpaired electrons. Clear? Okay? That's how you have to answer that question. Now, next one, FeCN6 3 minus is weakly paramagnetic. You can understand this one when paired with the previous one. Previous one is what? Here it is water, which is a weak field ligand, right? Now, same situation in FeCN6 3 minus. Here also, Fe is in plus 3 state, right? X plus minus 1 into 6 minus 6 is equal to minus 3. So, Fe is plus 3. That is, Fe is in ferric state. So, what is Fe3 plus? It is argon 18 and 3d5. So, here what happens is, there are 5 unpaired electrons. This is 3d. Then 4s is empty. 4p is empty. Now, what is the difference between the previous complex and this? Previous one was water, which is a weak ligand. But here cyanide, which is a very strong ligand. So, it will force pairing. When it is forcing pairing, what will happen? These are 5. So, 1, 2, 3, 4, 5. Right? So, it will become 2 pairs and a single electron. Now, these 2 will go with, see, it will become D2sp3 hybridization, making it octahedral. Fine. But coming to the magnetic nature, there is only 1 unpaired electron here. 1 unpaired electron means it is weakly paramagnetic. Clear? It is the board question in one of the recent latest papers. Okay, practice that. Now, next question. CONS3 6 times 3 plus is an inner orbital complex. This we have already completed, so I'm not going into detail again because ammonia strong ligand forces pairing. So it is D2sp3, inner D is involved. So it becomes inner orbital complex. But this one I will explain to you because it is an exception. This is already done, so I'm not going to that. It is D2sp3. Let's come to NiNS3 6 times 2 plus. X, ammonia is 0, so nickel is in +2 state here. X plus 0 is 2, right? Now coming to nickel 28, argon 18, 3D8 4s2, that is nickel. Then what is nickel 2 plus? It is argon 18, 3D8. Now please do understand that whenever nickel 2 plus is a D8 ion. Whenever you have Ni2 plus D8 ion coming in octahedral coordination, it is an exception. Register it properly. If it is coordination number 4, no problem. But when it is coordination number 6 and nickel 2 plus means it is an exception. Therefore, it is commonly asked in both papers also. Let's see what is the exceptional character here. Now 3D8, look here. I'm just going to explain it. 1, 2, 3, 4, 5, 6, 7, 8. So there are 2 unpaired electrons here, you could see. Now 4s, 4p. Just listen well. You can see what is the exceptional character here. It is octahedral coordination. Octahedral means you need 6 hybrids. Coordination number is 6, right? So it should be D2sp3 or sp3d2, right? Now, ammonia is a strong ligand. Ammonia is a strong ligand. Suppose it forces pairing. If it forces pairing, look here, this is going, it is going from there and it is getting paired here. 3D8 becomes 4 pairs. But unfortunately, it is able to vacate only 1 d orbital. Do you think it can help in an octahedral setup? It should be D2sp3. Only 1 d is vacated. If it was coordination number 4, we could use dsp2. Fine. But coordination number 6 means this change is not helping this complex in any way. So what will happen? It will remain in the same way, okay? That is, it will remain in the same way because even if it is pushed inside, nothing is happening. That is, it is not getting, even if it is getting paired, what is happening? Only 1 d orbital is getting vacated, which is not useful in octahedral coordination. So leave it there. We are not taking it. It is going to sp3d2 hybridization. I hope it is crystal clear why it is going to sp3d2, why not d2sp3. Even if a strong ligand is there, it is not going to, it is not getting benefited. Understand, the complex is not getting benefited. So it is sp3d2 hybridization and it will be paramagnetic with 2 unpaired electrons. Clear? Understand? So actually the nature of the ligand, whether strong or weak, doesn't matter here in this particular case because it is octahedral coordination with a D8 ion. Keep it in mind. Okay? So this NiNS3 6 times 2 plus or NiH2 or suppose water is their weak field ligand, then also it will not force pairing because it is not going to help in any way. Understand? Weak field ligand anyway will not force pairing. Even if it is strong, even if it is forcing pairing, it is not of any use. So what you have to register, whenever nickel 2 plus comes in the question with coordination number 6, whatever be the nature of the ligand, it will be always undergoing sp3d2 hybridization. Means it is always an outer orbital complex. There is no chance that it will become inner orbital complex if nickel 2 plus is in octahedral coordination setup. Clear? Okay. Now we are going to take another complex. NiCN4 2-. It is square planar and diamagnetic. If you understood the previous cases, this should be very simple for you. Same case, it is Ni28, argon 18, 3D8, 4s2. That is, nickel is the central atom, whose atomic number is 28. And here X plus minus 1 into 4 is equal to minus 2. So here also nickel is in plus 2 state. So it will be argon 18, 3D8. But here it is fine because it is D8 Ni2 plus, but coordination number is 4. So it is okay. So only when it is 6, it is exceptional. Okay. So 3D8. 1, 2, 3, 4, 5, 6, 7, 8. Then 4s and 4p. Understand, coordination number is 4 means it will be tetrahedral or square planar, sp3 or dsp2 hybridizations. Because 4 means you need 4 hybrids, means you have to mix 4. sp3 or dsp2. Clear? Remember like that. So, here cyanide is a strong ligand. So what will happen? It will force pairing. This will be pushed inside. So this orbital is vacated. So it can undergo dsp2 easily. That will be the hybridization. Understand? So next step, you will write these 4 together and these 4 together. That is, next step figure will be like this. These 4 together after detaching one D. Now 1, 2, 3, 4. These 4 hybrids together. Okay? 4 hybrids together, 4 dsp2 hybrids together. And this unused 4p separate. So this will be the setup. Now you will draw 4 pairs of electrons here. They are the 4 pairs of electrons coming from 4 cyanide ion ligands. And that is the situation. What about the magnetic nature? If you look at this part, there are no unpaired electrons. So it will be diamagnetic. Clear? Okay? That's how you have to do. And what will be the shape? dsp2 hybridization means it will be square planar. If it is sp3, it will be tetrahedral. Clear? That's what you have to do in this case. So this is square planar because hybridization is dsp2 and it is diamagnetic due to the absence of unpaired electrons. Clear? Okay. Now coming to the next one. Same thing, Ni2 plus here, but the difference is chloride ion is the ligand. It is a weak ligand, so it cannot force pairing. So what will be the situation here? Here also it is Ni2 plus when you calculate, which is argon 18 3D8. So it will be 3D8. 1, 2, 3, 4, 5, 6, 7, 8. Then 4s empty, 4p empty. That's the situation. So this is 3D, this is 4s, and this is 4p. Now what will happen? This chloride ion is a weak ligand. I hope you people know why these halide ions are weak ligands, because they are highly electronegative. So they will try to retain the electron pairs with them rather than giving it away to the central atom. So they will be poor donors, so they will be poor ligands, weak ligands. Get it? Okay? So, chloride ion is a weak ligand, so it cannot push this electron inside. No pairing takes place. So, 1, 2, 3, 4. So, it will be sp3 hybridization. If it is sp3 hybridization, the shape will be tetrahedral, right? And what about the magnetic nature? It is paramagnetic because there are 2 unpaired electrons here. Understand? So this is the difference between previous complex and this complex. Previous one was square planar and diamagnetic. This is tetrahedral and paramagnetic. If you go to the shape, it will be Ni, then Cl, 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 and 2-. This is the tetrahedral NiCl4 2-. Clear? Previous one, if you want to see the shape of this complex NiCN4, it will be like this. Ni, it is square planar. So Cn, 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 Cn and 2 minus. That's it. Clear? So such questions are very common in papers. That's why we are taking quite a few examples. Now next one, NiCl4 2 minus is paramagnetic, while NiCO4 is diamagnetic, though both are tetrahedral. Both are tetrahedral means both are sp3 hybridized. Then how come this is paramagnetic and this is diamagnetic? This case I'm not going to redo because we have done the same question here. NiCl4 2 minus is paramagnetic. Now the same thing is here, so you know it is paramagnetic. Now let us take this complex, NiCO4. It is a carbonyl. Carbonyl means it is again exceptional. Carbon monoxide is a very strong ligand. You know that. So, and next exception, there are two exceptional characters what you have to apply here. One, CO is a very strong ligand. Second, in metal carbonyls, metal will be in zero oxidation state. You don't have to calculate it. It is zero. Okay? Understand that. So nickel, it is 28. So it is argon 18, 3d8, 4s2. And it is nickel 0. Means what? No electron is lost. So all of them will be present. Okay? No electron is lost. So it is 3d8. 1, 2, 3, 4, 5, 6, 7, 8. 4s is also there. It is not lost. It is there. Then 4p and 4d is there. Okay, so this is 3d, 4s and 4p. So we have applied the first exceptional feature, that is the metal is in zero oxidation state. So s electrons are also there. We have applied that. Second exceptional feature is carbon monoxide is so strong a ligand that even these s electrons are forced inside. So what will happen now? These electrons are also, these electrons, there were 2 electrons here. They are also pushed inside. So they will come here. Now the net result is, it was 3d8 4s2. Now those 2 electrons also came here, making it 3d10 now. That's the present situation, present status of the complex. Okay. So now these 3 orbitals, this 1 orbital and these 3 orbitals are empty. So they will undergo sp3 hybridization. Now what happens is, s electrons are pushed inside. In NiCN4 2 minus, d electrons were pushed inside, vacating inner d. So it went to dsp2. But here s electrons are pushed inside. So this s becomes free now and it is becoming sp3. Tetrahedral shape. And look at this inner part. There are no unpaired electrons. So it becomes diamagnetic. So understand, this is tetrahedral and diamagnetic here. But previous case, it was also tetrahedral, but it was paramagnetic. Understand? These are all recent board questions. Okay? Make sure to prepare. Now, the next question is, predict the number of unpaired electrons in the square planar PtCN4 2 minus ion. It is an index question, but it's very important. So, I thought of discussing it with you. Here the central atom is Pt. You know that. So, X plus cyanide is minus 1 into 4 is equal to minus 2. That means Pt is in plus 2 state here when you calculate, right? So, Pt, it is 78. Better to know the configuration of platinum because it is not so commonly used in your syllabus, but some questions are there like this where you will have to use it, so better to practice. Okay? So, platinum 78. Configuration is xenon 54, 4 of 14, 5d9, 6s1. This is the configuration of platinum. Okay? Now, what is Pt2 plus? Pt2 plus is xenon 54, 4 of 14, then 5d8, 8 because this electron is lost, this one electron is also lost. Basically, it is a D8 ion. D8 ion, just like nickel. Okay? It is a D8 ion, nickel 2 plus. Similar to that. So, now D8 ion means what? D8 ion means it will be like this. I'll just draw it here. It is 5D8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Then after 5D8, there is a 6S and P also. Now, Cn minus is a strong ligand, so it will force pairing. Just like NiCN4, okay? It will force pairing. So, this will come here. This is forced inside. It will come here. Understand? So, it becomes 5D8 like this. Now, it will be DsP2 hybridization. DsP2. So, it will be square planar. But question is, predict the number of unpaired electrons. Some students think, oh, predict the number of unpaired electrons. There will be some unpaired electrons. So, 1, 2, 3, 4. You have to get a sub number like that, right? But here, your answer is 0. There are no unpaired electrons in this complex. Clear? So, always make sure to work it out and see how many unpaired electrons are. Clear? Okay. Now, next question. Another exceptional one. Describe the state of hybridization, shape and magnetic behavior of the following complexes. This one and another one is following. Now, let us start. A commonly asked question, exceptional. This is X chromium, water 0, oxalate, each oxalate is -2, -2 into 2, -4 is equal to -1, the charge on the complex. So, you are getting X is equal to +3. That means here chromium is in +3 oxidation state, right? Now, what is the configuration? Chromium is 24. It is argon 18. You have studied in 11th standard. It is 3d5-4s1, not 3d4-4s2. So, you are not supposed to write like that. You have to write 3d5-4s1 itself. Now, what is Cr3+? Cr3+ means it is argon 18. And 3d3, 1 electron from here, 2 more from here. So 3d3. Now, you can see how it becomes exceptional. 3d3 means what? 3 electrons are here. Now 3d3, 4s is empty, 4p is empty. So this is 3d, this is 4s, this is 4p. Right. Now, water is weak ligand. But oxalate is a strong ligand. It can force pairing. But, oxalate normally acts as a strong ligand only with cobalt. Here the central atom is chromium. In fact, the ligand has no say here in this complex. Whether it is strong or weak, I told you oxalate is acting like a strong ligand mainly only with cobalt. Here it is chromium. But, does it matter? Because whether it is strong or weak, we don't mind in this case. You know why? If the complex is octahedral, it can be D2sp3 or sp3d2. And the nature of the ligand matters only when you have to force pairing or something like that. Here, why it becomes exceptional? Already 2 orbitals are free. That is, you don't have to do anything. Cr3+ doesn't need the help of anybody. It is already having 2 empty orbitals. So it doesn't matter whether the ligands are strong or weak, not a matter to me. Understand, that is the mentality of Cr3+ here. So it will go straight away for D2sp3 hybridization. 1, 2, 3, 4, 5, 6. So whenever Cr is in Cr3+ state and coordination number is 6, it will straight away go for D2sp3 hybridization. It will be always, irrespective of the nature of the ligand, it will be always inner orbital complex. And it will be paramagnetic with 3 unpaired electrons. Clear? So, discuss the state of hybridization. It is D2sp3. Shape, octahedral. And magnetic nature, it is paramagnetic with 3 unpaired electrons. Clear? So, we have discussed some exceptions. Once I complete this, I'll just, recap all those exceptions quickly. Now, what about the next one? CONS3 twice, En twice, 3 plus. Here, cobalt is the central atom. And cobalt is 27. So, it is argon 18, 3D, 7, 4s2. Here, X, 0, 0. So, X is plus 3. That means cobalt is 3 plus. So, it is argon 18 and 3D6. So, 3D6. 1, 2, 3, 4, 5, 6. Then 4s and then 4p. Okay? Now here, again coordination number. Some students think coordination number is 4. They take it 2 plus 2. But En is a didentate ligand, right? So 2 into 2, 4 plus 2, 6. It is octahedral. So it will be D2sp3 or sp3d2. So that means you have to check the nature of the ligand. Ammonia strong ligand, En also strong ligand. So they will force pairing. What will happen? 3d6 will become, this will come here, this will come here. So these two orbitals are vacated. So D2 sp3. So the hybridization will be D2sp3, shape octahedral, magnetic nature will be diamagnetic. Clear? Next step, you can draw these 3 together and these 6 together. They will be the hybrids. Right. Okay? So that's all about the valence bond theory area. Okay? Now we are going to see crystal field theory in detail. Let's see what are the postulates, important points under CFT. In crystal field theory, we take the metal ion to ligand bond, metal to ligand bond as ionic in nature. And it arises out of electrostatic attraction between the metal ion and the ligand. Okay? And the 5 d orbitals in the metal, central metal atom or ion, they are supposed to be degenerate. You know, dxy, xz, yz, x square, y square, z square. These orbitals are of the same energy, degenerate, provided it is surrounded, the metal ion is surrounded by a spherically symmetrical charge cloud. Then they will be degenerate. But when this electric area, that is electric cloud, the negative cloud, is because of ligands, these 5 d orbitals will not be of the same energy. They will split into 2 sets called T2G and EG, or T2 and E, depending on whether it is octahedral or tetrahedral crystal field. That is dxy, yz and xz. You know, these orbitals are in between the axes. The double dumbbells are in between the axes. If you remember, it will be like this. dxy, yz, xz. If this is x and y, you know, it is like this, isn't it? You have studied it in 11th standard. This is xy and this is x and z will be xz. If it is y and z will be yz. Basically, in these 3, the double dumbbell lobes are between the axes. So they will be behaving in a similar way. That is, all these will be like this, isn't it? Only thing, axis labels will be different. It can be yz and this is xy, so it can be xz. You can label like that. So these 3, the double dumbbells are in between the axes. So they will behave in a similar way. Whereas the other 2, x square, y square, x square, y square, or dz square. These are all on the axis, you can see. So these 3 will behave in same way. These 2 will behave in same way. So when the electron cloud is because of the ligands, the otherwise 5 degenerate d orbitals, they were of the same energy in isolated gaseous metal ion or free metal ion. All of them, means in the absence of ligands, all of them were having the same energy. But in the presence of ligands, these 5 d orbitals will split into 2 sets. These 3 will make 1 set. These 2 will make 1 set. So this will be called T2G if it is octahedral field, and this will be called EG if it is octahedral field. It will be called T2 if it is tetrahedral field. It will be called E if it is tetrahedral field. That is, there is no subscript G in tetrahedral field. Understand? So this happens, this is called crystal field splitting, and this happens only, that is the d orbital splitting happens only in the presence of ligands. This phenomenon is known as crystal field splitting, and the energy difference between these two levels, T2G and EG, or E and T2, that is called crystal field splitting energy, CFSE. It is indicated by delta O or delta T if it is octahedral or tetrahedral field respectively. Clear? Now, so these are the main postulates of crystal field theory. Now, d orbital splitting diagrams. You know, you have 2 diagrams in your textbook. One for octahedral field where T2G is down, EG is up. T2G is having lower energy than EG. Practice that figure. Similarly, in tetrahedral field, E is below T2. Means E is having lower energy than T2. Practice those figures with labels perfectly well. Okay? They are previous board exam questions. Now let's see what is spectrochemical series. Spectrochemical series means the arrangement of various ligands in the increasing order of their crystal field splitting energy or increasing order of their field strength. Meaning going from weak field ligand to strong field ligand in the increasing order of their field strength. That arrangement is called spectrochemical series. It is a repeated board question. Spectrochemical series is given in your textbook. Learn that order properly. Means when they ask you the question, define spectrochemical series. In addition to the definition, try to write the series also if you aim a perfect score. Clear? Okay. Then CFSE definition I told you, it is the difference in energy between T2G and EG. The energy difference between the 2 sets after splitting of d orbitals. That is called crystal field splitting energy. That is also important. Then d orbital configurations based on comparison of CFSE and pairing energy. We will be doing some questions shortly. Now, let's come to this question. Hexa aqua manganese 2 ion contains 5 unpaired electrons, while hexa cyano ion contains only 1 unpaired electron. Explain using CFT. Using crystal field splitting energy, you have to explain this. Let's see how to do it. Hexa aqua manganese 2 ion. What is hexa aqua manganese 2 ion? Mn S2O 6 times 2 plus. Hexa aqua, this is 0, manganese 2, so 2, 0. So 2 plus will be there as the charge on the ion. This is hexa aqua manganese 2 ion. Whereas, so this has 5 unpaired electrons, they are saying. This is a board question. And hexa cyano, that's the old usage, cyanido is the latest. So hexa cyanido, it is manganate ion because it is manganese. So Mn, then hexa cyanido. So it will be manganate ion. Okay, it will be 2 minus 6. So it will be minus 4. So this has only 1 unpaired electron. They are asking you why it is like this. Hexa aqua Mn2 manganese ion has 5 unpaired electrons. Hexa cyanido ion has only 1 unpaired electron. How will you explain it? You can see here Mn is 2 plus. Here also Mn is 2 plus. So let us come to Mn. 25. It is argon 18, 3d5, 4s2. This is the configuration of manganese. And what is Mn2 plus? Mn2 plus is argon 18 and 3d5. That means it is a d5 ion. So manganese 2 plus is d5 ion in both of them. Then what's the difference between these two? This is a weak field ligand, cannot force pairing. This is a strong field ligand which can force pairing. So how will you draw it? Look here. If you look at the splitting diagram, and you can see it is octahedral coordination. So, in the energy diagram, T2G will be down and EG will be up, because T2G is having lower energy than EG in octahedral field. And the difference in energy between this is called crystal field splitting energy in octahedral field, that is delta O. Now I have to take D5 ion. D5 means I am going to fill this, okay? Because you have to explain according to CFT. So it will be, I am going to fill 1, 2, 3. You know, when you fill this, you have to follow Hund's rule, right? So fill, these are having the same energy, fill them one each. Then only pairing will take place. But, you know, here, now I have to fill totally 5 electrons, 1, 2, 3. Where to put the 4th electron? Look at the nature of the ligand. It is a weak ligand. Weak ligand means it cannot force pairing. That means when you compare delta and P, then it is a weak ligand means it cannot force pairing. Pairing energy and delta O you have to compare. If it is a weak ligand, delta O will be less. Okay, the gap will be less. Pairing energy will be more. If pairing energy is more, pairing cannot take place. That means for a weak field ligand like water, pairing energy will be more than delta O. Pairing cannot take place. Or delta O is less, so 4th electron will go here. 1, 2, 3, 4, 5. So what is the configuration? It will be T2G3 and EG2. So you can see there are 5 unpaired electrons if it is hexa aqua manganese 2 ion. There are 5 unpaired electrons because water is a weak field ligand. No force pairing, pairing energy is more. This is the situation. But if you look at this, cyanide is a strong ligand. So how it will change? If cyanide is a strong ligand, what happens is, strong ligand means what? The repulsion will be more between T2G and EG. The gap will be more. That means this delta O will be greater than pairing energy. So pairing will take place because pairing and the price of pairing is less. Pairing energy is less means pairing will take place. Gap is more. So what will happen to the 4th electron? What will happen to the 4th electron? Here, in these 2 orbitals, what you are going to do is 1, 2, 3. Now 4th one, will it go here? No, because this is far away. Gap is more. So pairing energy is less means pairing will take place. Instead of going to the higher side, it will get paired here. 1, 2, 3, 4, 5. Pairing takes place because cyanide is a strong ligand. Forced pairing happens for a strong ligand. Pairing energy is less than delta O, than the crystal field splitting energy. So pairing will take place, resulting in only 1 unpaired electron. So you have to understand, in both of them, it is D5 ion. But the difference is, here, weak ligand, weak field ligand, no force pairing, so it was T2G3, EG2. Now here it is T2G5 and EG0. That's what's happening. So here there will be only 1 unpaired electron. Understand? Practice well. Next one is bonding in metal carbonyls. I have told you bonding in metal carbonyls is special, that metal is in zero oxidation state and carbon monoxide is a very strong ligand. It forces pairing, including the 4s electrons inward. Okay? So keeping those things in mind, we are just going to see the figure explaining bonding in metal carbonyls. And there is a paragraph in your textbook which you have to learn by heart along with the figure. So we'll have a quick explanation on what is the status of bonding in metal carbonyls. Look here. Suppose this is the metal atom. Okay? And I am drawing its orbitals. Symbolic presentation. And I am going to draw, if you remember, the hybrid orbital. Okay? Suppose this is the hybrid. Just a symbolic presentation, that's all. And when you come to carbon monoxide, okay. Carbon monoxide, it is C triple bond O. Okay? These are the orbitals on carbon monoxide. Now, we are going to see what is the connection between metal and carbon monoxide and how it is done. Here, if you remember what we have done before in metal carbonyls, that is a VBT concept, we have seen that the carbon monoxide ligand, the lone pair on carbon in carbon monoxide, will be given to the vacant hybrid. The green color what I have drawn here is the vacant hybrid orbital. Okay? That is, the ligands are giving their electrons to the vacant hybrid orbitals, if you remember. So, that is the ligand to metals vacant hybrid. This is a sigma bond. This is the sigma bond. From ligand to metal, it is a sigma bond. Normally, in most of the complexes, this is the only bonding what is happening. That is, there is a sigma bond between ligand and the metal. Ligand is giving electron to the metals hybrid, and that is the sigma bond. Normally, it ends up there. But in metal carbonyls, there is a back bonding also. And what is that back bonding? We are going to see. And that bonding is, you know, these are the metals orbitals, right? Filled orbitals. Now, these are the molecular orbitals, representation of molecular orbitals of carbon monoxide molecule. Now, from these filled orbitals, these are the filled D. If you remember, the inner D, for example, 3D was filled. Okay? It was completely filled orbitals in metal carbonyl after pushing the 4s electrons also inside. So, from the filled orbitals, electrons are back bonded, means they are given back to these empty molecular orbitals of carbon monoxide. That is half above the plane, half below the plane, which is a pi bond. So you can see there's a back and forth type of bonding in metal carbonyl. In normal complexes, it is only this one happening, ligand to metal. Here also, ligand to metal, that is, from the ligand, the electrons are given to the empty hybrid, vacant hybrid orbitals of the metal. So that is the normal sigma bond. But here there is a back bonding also happening in metal carbonyls. And that is a speciality of the carbon monoxide ligand. So from the filled d orbitals of the metal, electrons are given back into these vacant molecular orbitals in carbon monoxide molecule. So such a bonding, back and forth type of bonding, that is called synergic bonding. Okay? So this is the speciality, and that is why carbon monoxide is acting like a strong ligand, very strong ligand, because of this synergic bonding present in metal carbons. Clear? Practice this figure well and the associated paragraph from the textbook. It is a very important, sometimes it comes for 3 marks. So prepare well. Now, coming to structure of metal carbonyls. Some of the metal carbonyls, you have to learn the structure. They are also there in the textbook, like nickel carbonyl, then tetracarbonyl nickel 0, pentacarbonyl iron 0. You know, metal is always 0 in metal carbonyls. Some of them we will have a discussion. If it is tetracarbonyl nickel 0, you have studied it is tetrahedral. So you'll be asked to draw it like this. Ni, CO, 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 CO. This is the structure of tetracarbonyl nickel 0. If it is FeCO5, that is pentacarbonyl iron 0. How will you draw it? Iron, it is actually trigonal bipyramidal. Okay, so CO, 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 CO. So it is trigonal bipyramidal. Okay, so all these are there in the textbook. Please practice. Then hexacarbonyl iron 0, all those, the chromium 0, all those you have to practice. Okay, so please take it from the textbook. I don't think we have to spend time on that, all these structures. And now, next one, we are going to discuss some of the important board questions asked in recent papers. How many ions are produced in the solution from the complex NiNS3 6 times Cl2? In the beginning of this session, I have told you the difference between complexes and double salts, isn't it? Apply it. You know this is a complex. So when you put NiNS3 6 times Cl2 in water, it will this will be one intact unit. So it will be Ni, means it will not dissociate further into the inner ions, or ammonia will not come out. NiNS3 6 times 2 plus, because chloride ion is minus 1 into 2 minus 2, to cancel this is plus 2. So plus 2 plus how many chloride ions are there? 2 chloride ions. Each one is minus 1. So there are 2 chloride ions. I hope it is clear how you write the ionization. So how many ions are produced when this is dissolved in water? You get this complex ion plus 2 chloride ions. So 1 plus 2, totally there are 3 ions. Clear? Practice. Then, which of the following is the most stable complex? I have told you something called chelate effect. Whenever chelate ligands are there, means more than one denticity, like didentate, then tetradentate, hexadentate, such ligands are there, then tridentate, terdentate, all these. Then there is an enhanced stability that is called chelate effect. So, all these are unidentate ligands. But when you come to this, it is a didentate ligand, which will give extra stability to the complex through chelate effect. So, whenever chelate ligand is there, that will have a chelate imparted stability. So, that is called chelate effect, which will have extra stability. So, that's the answer. Now, next one, which of the following species is not expected to be a ligand? Which is not expected to be a ligand? Carbon monoxide, ammonia, water, all these are ligands. This is a positive entity, normally not acting as a ligand. So, this is the answer. These are all latest board paper questions. Yeah, this question is a bit tricky, and it is a trendy question in recent board papers. Let us solve it. When a coordination compound, NiCl2 is mixed with AgNO3 solution, 2 moles of AgCl are precipitated per mole of the compound. Write the structural formula of the complex and the secondary valency for nickel ion. See how to do it. What is the formula of the compound given? Ni. This is a very simple question. Apply in the right way, that's all. We'll make it very simple. NiCl2 6 water. You are told that 2 moles of AgCl are precipitated per mole of the compound when you add silver nitrate. When you add silver nitrate, Ag plus of silver nitrate will combine with chloride ion to form silver chloride, which is appearing as the white precipitate. So if 2 moles of AgCl are precipitated per mole of the compound, it means that 2 chloride ions are there as counter ions, which are ionizable and present in the solution. Okay. So what we are going to do is, okay, let this be the complex. 2 chloride ions are outside. They will come out in the solution as 2Cl minus, which will combine with 2 Ag plus to form 2 AgCl. Clear? Now, remaining part, nickel is the central atom. So these 2 chloride ions I have used as counter ion. Remaining what is there? 6 water molecules. So nickel's coordination number here is 6. It is associated with 6 water molecules. Nickel can show coordination number 4 and 6. Do you remember NiCO4, NiCN4, NiCl4, etc.? So, and NiS2O 6 times, NiNS3 6 times. Okay, 4 and 6, both possible. So, in this particular case, out of this, you remove 2 chloride ions outside as per the data given, hint given, and 6 water molecules will be inside. So, what is the name of this complex? Hexa aqua nickel 2 chloride. Okay, minus 1 into 2 minus 2 to cancel this is plus 2. So, X plus 0 is 2. So, nickel is 2. Hexa aqua nickel 2 chloride. So, this is the formula of the complex, or this is the structural formula of the complex. NiS2O6 times Cl2. That is the complex formula. And so, write the structural formula of the complex. This is the structural formula. And what is the secondary valency? Secondary valency means it is a coordination number. Here coordination number is 6. Clear? That's it. Now, write the IUPAC name of the ionization isomer of this one. We are checking your ionization isomerism concept. What is ionization isomerism? Counter ion will become the ligand. Ligand will become the counter ion. Remember that? Exchange. So, what will be its ionization isomer? This is the compound given to you. Create its ionization isomer. So, CO, NS3 5 times. Pull chloride in and put sulfate out. We are exchanging the anionic ligand and the counter ion, which is anion. And then you have to name this by the IUPAC name. This is minus 2, sulfate charge is minus 2. To cancel that, this is plus 2. Let us calculate X, 0, minus 1. So, X plus minus 1 is equal to 2. X is equal to plus 3. Here, cobalt is 3. What is the name? Pentaamine. Pentaamine. Yeah. Then chlorido. Chlorido. Then cobalt. Because the complex is positive, you have to write cobalt, not cobaltate. Cobalt 3. That is what we got. And then counter ion is sulfate. That's it. So that's the name of the complex. Clear? Name of the ionization isomer of the complex. Then, using valence bond theory, predict the geometry and magnetic behavior of. These are all discussed in the class already. I just have given it as a board question, latest as in 2023 CBSE paper. Practice them. We have already done in this today's session itself. Okay? So, please recheck. Next one, give reason. Low spin tetrahedral complexes are not formed. What is the meaning of low spin? Less number of unpaired electrons, more number of paired electrons. So, tetrahedral complexes. Look here. I have told you what is tetrahedral complex. In tetrahedral complex, you know, EG down or E down, T2 up. Okay? This is how the splitting happens. And this is delta T, which is the CFSE, crystal field splitting energy in tetrahedral field. And tetrahedral coordination means only 4 ligands. Octahedral means 6 ligands are there. So where the splitting will be more, when you compare same ligand, you will have delta T is only 4 by 9 of delta O. Means when you compare this gap, it is less, it is only 4 by 9 of what is there in octahedral splitting. Means the gap is lesser in tetrahedral splitting compared to octahedral splitting. So what will happen? Suppose I fill 2 electrons here. The third electron will automatically go here instead of getting paired. What is the reason? Because the gap is very less. Gap is only 4 by 9 of delta O. So it will go there. Next one will come here. Next one will come here. Then only pairing will take place. That means it will lead to a high spin situation because the gap is less. If the gap is more, pairing will take place and you will get low spin situation. Question is, low spin tetrahedral complexes are not formed. The low spin means if it is to be low spin, it should get paired here. Then only it will become low spin. But that will not happen because the gap is very less. It is only 4 by 9 delta O. That is why pairing doesn't take place. It goes to the upper level. Understand? So, number of unpaired electrons will be more. And how you have to write the answer in the board paper? It is a common question in recent board papers. Trendy question. Practice well. What is it? Low spin of tetrahedral complexes are not formed is the question. Answer. It is because delta T is only 4 by 9 of delta O. And hence the orbital splitting energies, means the CFSE, are not sufficient large enough. It is not large enough to force pairing. So it is not sufficiently large for forcing pairing. That is why pairing doesn't take place. So it will lead to a high spin situation, not a low spin situation. Clear? But at the same time, if it is octahedral, it will lead to low spin situation. High spin situation will be difficult to be seen. Understand? This is how you will get questions in the paper. This is commonly asked in assertion reason area also, so practice well. Next one, CONS3 6 times 3 plus is an inner orbital complex, whereas NiNS3 2 plus is an outer orbital complex. We have already discussed this in VBT discussion. Please recheck. It's already done. I have shown you that this is a repeated board question. Now, out of COF6 3 minus and COC2O4 thrice, which one is diamagnetic, more stable, outer orbital complex, low spin complex? How will you know? This is weak field ligand. So it will not force pairing. If it is not forcing pairing, outer D will be, because inner D is not available, outer D will be used. So it will be outer orbital complex. So which one is outer orbital complex? This one. Clear? Then if it is outer orbital complex and pairing is not happening in the inner D, there will be unpaired electrons in the inner D. We have done this complex already. So it will have paramagnetism. So which one will be paramagnetic? This is paramagnetic, but this one will be diamagnetic, because I have mentioned already oxalate is special when it comes with cobalt. When it comes with cobalt, oxalate acts like a strong field ligand. It will force pairing. So it is cobalt 3 plus means it is 3d6. Okay. Now it is forcing pairing means it will become 3 pairs. There won't be any unpaired electrons. So it will lead to diamagnetic nature. So diamagnetic will be this one. More stable will be this one due to chelate effect, because this is not chelating ligand. Then outer orbital complex will be this one. Low spin complex means what? Less number of unpaired electrons. Okay? Low spin or spin paired I have used in my explanation. So lesser the number of unpaired electrons, it is called low spin or spin paired complex. So here force pairing happens, so it will be low spin complex. Clear? That's how you have to arrive at the answer. Now, next one, although both NiCl4 2 minus and NOCl4 have sp3 hybridization, this is paramagnetic and this is diamagnetic. We have discussed this question also already, because we have discussed all these things in BBT area. Now, coming to the last question of the session. Write the electronic configuration of D5 ion on the basis of CFT when 1 delta O is less than P, 2 delta O is greater than P. We have done this question already in one of the previous questions, if you remember, that is hexa aqua manganese 2 ion. That one on hexa cyanido manganese manganate 2 ion. We have done that already. Same thing, but this is how it is asked in this paper in terms of D5 ion without giving any particular complex. So let's see how to do it. First of all, let us do delta O less than P. Because it is mentioned O, it is octahedral crystal field. So this is energy axis. If it is octahedral, T2G down, EG up. This is the gap, delta O, isn't it? CFSE. Now, let us start filling the electrons. D5, so 1, 2, 3. As per the Hund's rule, you have to fill one each, 1, 2, 3. Then where to put the fourth electron? Pairing energy is more. Pairing cannot take place. So fourth will go here because pairing cannot take place. Then fifth one here. So the configuration will be T2G3 EG2. If you are asked about magnetic nature, it will be highly paramagnetic. Not asked here, just mentioned. And then what about the next one? Suppose delta O is greater than P. Same energy axis, T2G, EG. Now let us fill the electrons. You know, P is less, means pairing energy is less. Delta is more, but pairing energy is less, so pairing will happen. Gap is more, so electron cannot go to the higher level. Pairing is easier. So 1, 2, 3. Fourth electron will not go there because the gap is more. Pairing easy, so it will come here, 4, 5. So what is the configuration now? T2G5, EG0. T2G5, EG0. That's the configuration in this case. Here it will be only less paramagnetic, weakly paramagnetic compared to this one which is strongly paramagnetic. Clear if it is asked. So like this here in this paper they have asked D5. In another set it was D4. Another set it was D6. Like that they will use different configurations in different sets. That's what I have seen. Okay. So practice all such questions well. And we come to the end of today's session. One shot on coordination compounds. I hope this session helped you a lot to get the ideas properly, how such questions are asked in the board papers and how to tackle them. Just practice again. It's just a matter of practice. See you inside for the next session and make sure to like, share and subscribe to my channel. See you inside for the next. Till then, bye.